say that that's philosophy. That's the world of philosophy. There is one kind of philosophy that I am especially interested in. And that's, for lack of a better name, mathy philosophy. It's very hard to say something more specific because really what unites the different problems that mathy philosophy is about is the fact that they interact with mathematics and more generally with the use of formal methods. So for example, the use of probabilities to model beliefs. So say that this is mathy philosophy. So if one is to talk about mathy philosophy, there are basically two options. Option one is to do it properly. So option one is to say, OK, there is this problem here that I want to attack. And if we did that, then this class would look like that. We would spend all semester doing the groundwork. And some of it would be brutally dull. And then finally, at the end, there would be this jewel. And it would be wonderful, but it would only be for the brave. So what I've decided to do is not do it properly. So there are all these delicious fruit within mathy philosophy. And what I'm going to do is I'm going to go straight for the fruit. I will try to be as rigorous as possible, given the methodology. But what that means is that sometimes, instead of giving a formal proof, I will give an informal proof and maybe point you to the place where the actual proof is. In some ways, that will make the class more difficult. Because if you have the details, if you have the proof, then you can go and check it. And the only thing between you and the fruit is work. Because I'm going to be informal and sometimes a little bit sloppy, between you and the fruit there will be work and also my sloppiness. So we're going to have to deal with it. And if you have questions, ask. And if you're unclear, go to section and talk to your TAs. But the advantage, the enormous advantage, is that you will leave this class with what, in my view, are the coolest insights that mathy philosophy has to offer. And some of them really are cool. So let me give you an example. One of these fruits is Gödel's theorem, which says, very roughly, we'll talk about it properly later, that you cannot give a complete axiom system for even baby mathematics, for arithmetic. Or more precisely, you can, but only if it's inconsistent. So only if it allows you to prove everything, including falsehoods. So that mathematical result is beautiful in itself. So it truly is one of the most beautiful theorems of the 20th century. It's certainly the most beautiful in mathematical logic. The proof has been fruitful in so many different ways. The result itself is mind-boggling. But I also think that it leads to these incredibly interesting philosophical conclusions. For example, when I grew up, this is how I thought of the edifice of knowledge. So I thought that there were less rigorous subjects and then more rigorous subjects, and maybe physics was very rigorous. And part of what that meant is that we had very good methods for establishing whether a hypothesis is true or not true. And then the king of rigor was mathematics. So I thought, when it comes to mathematics, we can be sure. So once you prove a theorem, you're sure. Now, it is commonly agreed that Gödel's theorem shows that that cannot be correct. And the reason, briefly, is that it's a consequence of the theorem that it's very, very hard to know whether an axiom system is consistent. So when you're working with an axiom system, there's always the risk that your basic principles are inconsistent. And this is not just speculation. It has happened. So it has happened that beautiful mathematical theories turn out to be inconsistent. And of course, if you're working on the basis of an inconsistent theory, then having proved something is no guarantee of anything, because in an inconsistent system, you can prove anything at all. So really, certainty in mathematics is relative to the assumption that we're working in a consistent system, and it's very hard to know whether we are or we're not. So the dream has been shattered. A lot of philosophy is like that. A lot of philosophy involves starting with some informal preconception of how the world is, and it's typically a very rosy idea, and then showing that once you think it through, things are not that simple. So we are going to look at many examples of that kind, and some of the other fruit are going to be that kind of thing. But there is also a different kind of fruit. So in some ways, infinity is the opposite. It is a natural thought that where finitude ends, absurdity begins. And let me give you an example of why some people have thought this. So suppose that you start with the natural numbers, and then you just throw 0 away. So ignore that one and just consider the rest. So if I were to ask you, which collection has more members, this one or that one? You would say, well, of course the first one, because it has all the items in the second one plus 0. So it has one more. But then there's another reasoning. You say, I can put these into 1-1 correspondence. I can just produce a mapping that maps that to that, and that to that, and that to that, and that to that, and so forth. So everyone will be assigned exactly one person from the other set. Nobody will be left out. So there is a sense in which there are just as many in the first collection as in the second collection. It's the same sense in which if someone is laying out a table and makes sure that next to every knife there's a fork, and next to every fork there's a knife, and it's always 1-1, then there are just as many forks as knives. So on the basis of this kind of consideration, many people assumed that we just couldn't reason coherently about infinity. And this is a case in which we're going to run in the opposite direction as Gödel's theorem. So here what is going to happen is that we're going to see that, in fact, there is a way of reasoning rigorously about infinity. It's very hard to find the right concepts with which to think about infinity. But once you do, it's amazing. Once you do, you generate this theory which will boggle your mind. So we're going to discuss it here. And a feature of the theory is that it's in some ways incomplete. So it's incomplete in that there are lots of important questions that are answered, but there are also things that we have no good answer to, and it's very hard to know how we would go about answering them. So there too we have sources of bamboozlement, and I want us to get clear about some of those. Okay, so the summary is we're going to go and try to find fruit. We're going to be kind of intuitive about the whole process, but the rewards are that you guys are going to discover some amazing things.